Alright, I'm going to try to scan these relatively fast here. Scan, quote unquote. Page 1. Very low-tech scanning. Hope it works. Page 2. Alrighty. Page 3. Of course, you have those pages already. I guess I don't really need to scan them. Here is the solution to problem 142. By the way, I'm not super happy about this problem. I'm probably only going to test the real one. I mean, if I ask a question about complex inner product spaces, I hope it's a more abstract question. Here it is. It's problem 144. This one wasn't too bad. Problem 145. More problem 145. Oh my goodness, this problem was awful. I may have an error in here. Hopefully not, but I'm not 100. I'm about 90% sure about the actual formulas here. This was much uglier than I wanted it to be. Here, anyway, this much should. I mean, I'm sure about that, but the specific formulas for x and y and x bar and y bar, I'm not so sure about. Anyway, so as I mentioned, integer eigenvalues on the test if there's one like that, and I mean this one involves using an online calculator, so it doesn't really make a very good test question. I'd have to give you information, right? This is, oh yes, here's a token bonus solution. That does make a nice quick test question, right? Find the matrix of the quadratic form. If you've done your homework, that shouldn't be a big deal. Let's see here. Oh my goodness. 147. Yeah. There it is. And the details of how to find the eigenvectors. Eigenvalue 1 gives you 2 linearly independent eigenvectors, and then eigenvalue 10 looks like gives you 1. Put those together, you got an orthonormal basis, and that gives us the formulas for coordinate change down here in the usual way. All right. There's one problem 148. Let's see, what is this? Ah, yes, this problem. So I'll give you guys hints about this one, a lot of you who asked me. Alright. I will scan this again at the department soon. Sorry about this stupid format, but my scanner is not so good. Anyway, there's the matrix. I checked the trace. I've not checked the determinant. Should be the product of the eigenvalues as well. I didn't check that. Let's see here. This one's actually a pretty nice problem. It just involves the notion of subset, of subspace, of the coset. There's something very useful about this problem. It's got a lot in it. Anyway, there it is. And then this problem, the part of it was okay. I mean, yeah, you get that this mod, the kernel, is isomorphic to the anisymmetric matrices, right? But the other thing I wanted to do here in terms of this being the direct sum of that, I need to know this, and then if I take the quotient of that, I get this. And I'm trying to do it the opposite way. I don't believe I have that theorem. I'm not entirely sure it's true. So, yeah, sorry about that. Here's the repair. To prove it's the direct sum, you just exhibit that any matrix can be written as a sum of symmetric and anisymmetric. And the only thing which is both symmetric and anisymmetric is a zero matrix. Consequently, Fn by n is the direct sum of Sn and An. And then problem 152. So again, sorry, I don't know where the theorem in my notes is I was talking about. My bad. 152, yeah, basically there's the matrix calculated in the usual way, and the theory says that the 2 by 2 block corresponding to the U basis is the matrix of the restriction of T, and then the matrix for the quotient is the other block, like that. And here's, for example, why that matches up with what you'd get from looking at the induced operator on the cosets, like so. Alright, obviously this wasn't required, I'm just commenting. And problem 153. Oh yeah, I gave you guys the setup of this mostly in class, I won't belabor this much. Talked about that in class for about 10 minutes already. There you go. I think linear independence is inherited from the dual basis, because it's a subset of the dual basis, which we already know is linearly independent. Alright, anyway. Oh, these are nice. So basically the point here is to recognize what subset means, ultimately. But there's that one. And here is that one. They're almost the same argument. I would say the difference is I felt obligated to prove the annihilator was a subspace, because we didn't do that yet, whereas I did prove that the perp was a subspace in class before, so you could use that. I will tell the grader to be nice if you haven't proved that they're subspaces. Oh, here's just a token extra problem. Whatever. And here is problem 156. It's got a lot of details, but it's probably worth understanding. Oops. And then here is this is expansion of the detail on the last page, basically. Oops. TIE fighters. Ever seen these? Kind of cool. I think it's going to break, though. I'm trying to record evidence of it before it's annihilated by a child's random action. Let's see here. Come on. And here's the rest of that. And then interestingly, we can rewrite a linear transformation in this language like this, which has other connections with our discussion of tensor products. But I'm not sure I have enough time or energy to make the connection as explicit as I'd like this semester. Sorry about that. Anyway, 157 is, oh yes, this problem. Basically, once you have that the matrix of S is the transpose of the matrix of T, if you just do like essentially think about pivot columns and pivot rows and such, you can work your way through it using just basically row reduction kind of technology to gain understanding about the null space or the column space of the matrix, and then consequently we know that the behavior of the matrix. If the matrix is full rank, then the mapping is surjective, and if the null space is 0, we know the mapping is injective. If you go back and look at what we developed for linear transformations, you'll see you can see whatever you need to see from the matrix about the transformation. They mirror each other. Anyway, so basically you just use the matrix argument. The transpose connects the columns and rows of one to the other. And then there's probably a way to make this even simpler. I don't know. I'm not entirely sure my argument down here is entirely necessary. Anyway. Ooh, this one. So, yeah, you're looking to find a vector such as trace of A is equal to AX, but that gives you trace of A is AX transpose by definition of the inner product, so the Reed's vector is just the identity matrix. Yep. In other words, the flat, see here in our musical morphism language, the flat of the trace is the identity matrix. And then this is a cute little problem, number 7, actually, of Demano and Little. I didn't tell you that, but it's true. And here's that. This problem actually has pretty nice little question. And the last problem. I hope you got that part. I hope you got this part too, if you can Google. The Google. And then there's this one. Actually wasn't that bad, right? Just one step at a time. This one I think uses the other steps before a little bit. Okay. And then finally, here we go. So there's the solution. I'll let you look at it. And then finally, it all kind of builds on each other, step by step, right? But there you go. So that is the solution. Sorry it took me so long to quote-unquote scan it. Anyway, I'll try to produce a actual decent scan tomorrow, as soon as I can. Sorry for the delay. Bye.